Okay, let's keep going here with Chapter 6 with Section 6.2, where we will talk about one-to-one functions and inverse functions. So first thing up, how do we figure out if a function is one-to-one? The key on this is that before we talked about every input has to have one and only output. Now that has to be reversed as well. All right, so every input has to have one specific output. All right, so this first one works, but the second one doesn't because 11 is coming from the cat and the dog. Not allowed. Every input has to have one independent output. All right, so a function is one-to-one if any two different inputs in the domain correspond to two different outputs. That's the key. All right, so every input has to have its own specific output to be one-to-one. All right. Now, one thing to keep in mind here is that each x in the domain has one and only in the range. All right, no y in the range matches up with more than one x, so clearly this one is out. All right, so the second one is not a one-to-one function, but it's still a function because every x has a specific y. But now here, the last one, we know that this is not a function because of x1. x1 has two different outputs, not allowed for a function. All right, so determine whether the following functions are one-to-one. The first one, certainly not, because of the Pontiac here, right? John and Andy both want a Pontiac, not allowed. And how about this one? No repeats in the x, so it is a function. Any repeats in the y? No, there's not. So this is a one-to-one function. No x repeats, no y repeats. All right, knowing that, try problems 9 and 13. Okay, so what we get to introduce now is the horizontal line test. So before we used the vertical line test to see if something was a function. If it also passes the horizontal line test, it is a one-to-one function. So this function here is not a one-to-one function because it fails the horizontal line test. So if we take a look, this one is one-to-one because any vertical line that we put through here would only touch in one spot. And clearly here, this is not a one-to-one function because it fails the vertical line test. Try problem 17. All right, so let's determine the inverse of a function defined by a map or a set of ordered pairs. So every input has an output. If we do the inverse, that flips. So the domain and the ranges flip. So student to car goes now from car to student for the inverse. So here, instead of Dan getting a Saturn, now the Saturn got Dan. All right, so we flip the direction. The inputs become the outputs. So our new function, the inverse here would be 5, 1, 8, 2, 11, 3, and 14, 4. All right, so what's the domain? The domain now is 5, 8, 11, and 14. Remember to put them in order. They were to begin with. The range now is the old domain, 1, 2, 3, 4. So you'll notice that when you do an inverse, the domain and range flip. Try problems 23 and 27. All right, so this is what we're saying before. The domain of f becomes the range of the inverse of f. Same thing with the range. The range of f becomes the domain of the inverse of f. So we get to flip them around. All right, so how do we verify that things are inverse functions? If you do the composite of them, you get x. All right, so let's test it out. So x cubed minus plus 2 is g, and inverse is, so now we're going to do plug in for here. We're going to do the cube root of x minus 2 cubed plus 2. Cubed and cube root cancel out. We've got x minus 2 plus 2. We get x. All right, we're in business. It's got to work both directions, though. So now we got to say the cube root of something minus 2. What's that something? X cubed plus 2. Those 2's will cancel. What's the cube root of x cubed? It is indeed x. And so we're in business. All right. Verify that the inverse is of these are, verify that f of x is the inverse of f of -1 of x, and then let's find which values we could use. So, plugging the inverse into f, we would have 2, 1 over 2x minus a half, and for x, plus 1. So this is f of the inverse of f. Let's clean this up. 1 over 2, and we would need a common denominator here. We would need to add an extra x here. So we would have 1 minus x over 2x plus 1. 2's cancel, and we've got 1 over 1 minus x over x plus 1, which we could make x over x for a common denominator. What happens when you have a minus x and a plus x? That's out of here. So now we've got 1 over x, which is the same as 1 times x over 1, which gives us x. All right? So what are the values of this? Remember, the domain down here is all real, but we have to look at what our input was. Up here, x could not be 0. Let's go the other way. 1 over 2 times x, which is 1 over 2x plus 1, minus a half. So now we've got 1 over, let's clean this one up first here. So this will be 2 over 2x plus 1. And then we're going to say minus a half. Okay, so this 1 over that would flip over, would become 2x plus 1 over 2 minus 1 over 2. So since we have a common denominator, plus 1 and minus 1 cancel, so now we have 2x over 2, which equals x. We're in business. What numbers can we use? Can't have 2x plus 1 in the denominator, so 2x plus 1 cannot equal 0. 2x cannot equal -1. X cannot equal -half. All right, lot going on here. If you're having trouble with this, we'll go over it in class for sure, but try 31. All right, objective 3, let's graph these things. Okay, so when you graph an inverse, it's reflected over the line y equals x. All right, so equidistant across this line. So you'll see here that the blue and the pinkish lines there, red, pink, are inverses of each other because they're reflected over the line y equals x. Okay? Notice here, A3, B3 becomes B3, A3. This is how you're going to graph it. You're going to switch. Remember, that's how we do inverses. Switch your x's and y's. So 1, 4, what does that become? That becomes 4, 1. 0, 3, what does that become? That becomes 3, 0. All right, -1, 0 becomes 0, -1. Right? And so if we connect these, let's look at our line. There, there, and there. Here's the line y equals x. Right? We would want to go connect here, and then connect here. And you'll notice that's the mirror image reflected about the line y equals x. All right, try to sketch out problem 41. Find the inverse of a function defined by an equation. Here's what we're going to do. Switch x and y. Okay, switch x and y. We're going to swap them out. So in this problem, originally we had y equals -1/3 x plus 1. The inverse is going to be x equals -1/3 y plus 1. We switch the x and the y. Get y by itself. Subtract the 1 times everything you see by -3. And there you go. You've got the inverse. You've got y all by itself. All right? Now, we could down here check the result by doing the inverse of each other. So we could say -1/3 of the inverse, which is -3x minus 1. Plus 1, and you should get x if you did this right. So what happens to -1/3 and 3? They're out of here. We're left with x minus 1 plus 1. Cancel those. We're left with x. We did this right. Okay, let's find this one. Let's find its inverse and then check the results. So the inverse here, we're going to have x equals 2y minus 1 over y plus 1. A little trickier here. Let's multiply both sides by y plus 1. So now we want to get y by itself. So let's distribute here, xy plus x. And then see if you can get everything that has a y with it on one side. So xy minus 2y over here, and negative x minus 1 over here. And now we're going to factor out. So we can factor out a y. We've got x minus 2 equals negative x minus 1. And let's divide both sides. Y equals negative x minus 1 all over x minus 2. You could clean that up to be negative x plus 1 over x minus 2. Looks a little prettier that way. Either way is fine. All right, let's check the result. Plug this back in to negative x plus 1 over x minus 2 minus 1 over negative x plus 1 over x minus 2 plus 1. All right, so let's get ourselves common denominators here first. So this one will have to be an x minus 2 over x minus 2. Same thing down here. This will be an x minus 2 over an x minus 2. All right, let's clean this up. In the numerator here, we have negative 2x minus 2 minus x plus 2. And then in the denominator, sorry, this is all over x minus 2. And down here we've got negative x minus 1 plus x minus 2. And this whole thing is all over x minus 2. The x minus 2's cancel. Let's see what else cancels. 2's. And we're left with negative 3x. And here we got the x's to cancel, and we're left with negative 3. Oh my goodness, look at that. We've got x. Those things are inverses of one another. Try problem 49. All right, 63. Find the domain and the range of this. Okay, so the domain is pretty straightforward here. The domain, x cannot equal negative 1, just from here. But what about the range? All right, and this is made easier if we would know what the inverse is. And fortunately, we solved that in the last problem right here. It's negative x plus 1 over, what was it, x minus 2. Okay, what's the domain of the inverse? The domain here is x cannot equal 2. And so we know that for f of x, the range is the same as the domain of the inverse. So the range is, y cannot equal 2, because the x's and y's switch. All right, so if we know the inverse, and we find the domain of the inverse, we know the range of the original function. Try problem 63. Okay, and then lastly here, we're going to find the inverse. If we restrict the domain, you'll see why we restrict it here when we finish it. Switch your x's and y's. Get y by itself. Square root both sides. So now we've got root x equals y minus 1. So root x plus 1 is going to equal y. And so in this case, we know that x is better be bigger than or equal to 1. Otherwise, we would get a problem in the square root. Okay? Do I agree with that completely? Yes, and we'll talk a little bit more about this in class. All right? But we're going to restrict the domain here because of what you can plug in. All right. Last thing, there's your summary, and we're good to go. Any questions we'll go over in class, and especially we'll talk about restricting domains for inverses in class. All right, try those problems. Good luck.